sign it just in case. It's a statement that you would allow me to use your image in case it got on one of the DVDs. And it's just a K-State project that we're doing, so I hope you'll sign, and thank you very much.
Yeah, Professor Bolland is what we call the Distinguished Teacher Scholar for the year. This is the major award. There's no higher award for teaching and the scholarship teaching you can get at this university. He's a very accomplished professor. Let's start. I've got an assignment up there. Let's make sure we understand that. Why don't I dim the lights just a little bit. There's a new assignment in blue at the very top. So chapter 8 is what I'll get into today. It's the chapter on rotational motion. I won't finish it today, but we'll certainly get a start on it. So there's your problem about that. Notice they're all exercises. I didn't assign any problems, you might say, as intuitive notation, but I did assign exercises. Also, I've got what remains of chapter 5. Remember last time we were going through the chapter 5 problems, and I didn't get to the last 3. So I wetted my finger and wiped out everything except for the last 3. Also, I've amended now, definitely be reading Bacon's Novum Organum. I'm going to talk about it today at the beginning of the lecture, but we'll talk about it again Friday too. So spread it out over 2 lectures. And then of course we got chapter 7. That's the chapter on energy that Professor Sakala lectured to you. When was that? Last Friday, I guess. We have to get to that. Okay, before we get into the lecture, let's remember that we're trying to keep our eye on the moon. Who saw the moon this morning? You got to remember this sense of wonder you got to have. You got to be looking at these things. You can make some. How about last night? Anybody see the moon? Great. Okay. Well, obviously your night viewing a lot more than you. I guess I was that way when I was an undergraduate student. Yeah, the moon rose about 9 o'clock last night. So it's rising later and later. That's the thing to notice. And since it's rising later and later, it's also setting later and later. Right now, at least in the morning, we've got our horizon here. So we got east, we got west, we got south. And when the sun is coming up, here's the sun. This is what, 6 or 7. I think the sun's coming up around 7 a.m. these days. I know I'm getting up in the darkness, which is particularly comfortable. And the moon is over here now, sort of in the southwest. It's kind of a gibbous phase, as it's called. And what I want you to keep an eye on now is that with time, every day when the sun's rising, this moon is going to keep working its way every day, another fraction of the sky towards the east. That's the same pattern we saw in the evening before the full moon when the sun was setting. It was also working its way towards the east. So with that pattern, we're eventually going to figure out what the heck the moon is doing in the sky, week and week and month after month. All right, let's get into the lecture. So I've asked you to read Bacon's Novum Organum, at least a part of it. And certainly I know it's a hard thing to read. Give it a good effort and pay attention to the words that this guy has to say. I think you'll see some relevance both for the science I'm trying to teach you and to using your mind in general. So who was Bacon? Well, his name was Francis Bacon. He was born, I don't know when, 1560. He died 1620. My mind, I basically remember 1600. This is when the guy was active, early 1600s. Who else was active in the early 1600s? Had a job at the bottom of the Tower of Pisa. Who was this guy? Galileo, right? Okay, so we got Galileo active around 1600. We got Bacon active around 1600. What did Galileo give us? The experimental method. Right? Galileo said, look, if you're really going to understand nature, you got to get out there and mess with it. You got to do experimentation, systematic experimentation, try to make some sense of it. Now, in many ways, that's what Bacon said too, but Bacon didn't do it. Bacon said, yes, if we're going to understand things, we've got to observe nature. But Bacon was a philosopher. What do philosophers do? They sit on their rear ends all day. They think, okay? So he was more like a theorist, right? He was thinking about things, getting good ideas, but he wasn't really doing them. still, the idea, it's new at the time, make observations. Now, what he lacked in his experimental abilities actually doing things, unlike Galileo who really did things, he made up for in the second step to the scientific method. And that's what this novum organum is about. Not only did he advocate making observations, but he also advocated a new way of thinking about them. Now, let's again put this in perspective. You're 21st century people, so it all seems straightforward to you. But back in 1600, we just had 1,500 years of Aristotelian physics, Aristotelian philosophy, dogma, authority, appeal to authority whenever you have a question, not appeal to observation, not appeal to trying it yourself to see what would happen. So the men's and women's minds had to be changed, and Bacon, his novum organum, was the prime instrument for that change. Another thing about Bacon is what a great time to live, Elizabethan England. Who else lived in Elizabethan England? Well, the easy answer is Elizabeth, all right? But beyond Elizabeth, we also had people like Shakespeare. Okay? If you remember your history, you might remember the English defeat of the Spanish Armada in late 1500, 1588, I think I remember. Okay? That basically gave England the power of the seas. And of course, trade and commerce was the golden age for England. And it goes right up to this day, because of course we have a great English culture. So Bacon was right there at the beginning regarding all this intellectual foment that's going on. Well, okay, so let's get into a little more detail here on Bacon. One quote that I particularly like, which is only partially relevant to what I have to teach you about the science of Bacon, but it's a good one anyway, so I'll read it to you. The monuments of wit survive the monuments of power. Isn't that great? Yeah, in other words, the use of the mind is much more than the use of the arm or the sword. And that's why you come to the university, to learn wit. He also wrote, and here's the key thing, that his purpose was, quote, to try whether I cannot, in very fact, lay more firmly the foundation and extend more widely the limits of the power of the greatness of man. See, isn't that just a noble endeavor to extend the limits and the power of man? It's also marvelously arrogant. Who of us can actually think we could actually do such a thing? Bacon had a marvelous mind, so we could do it. Let's see. He was compelled to review the whole intellectual history of mankind to see why, and this is a good term, why philosophy had been so productive of words, but so barren of fruit. Yeah, for years people have been sitting around thinking about things. Where? In the cloistered halls of churches and monasteries. Medieval philosophy is essentially the work of cloistered men cut off from reality. Instead, they have to get out into reality and look and see what can be discovered. To quote another modern-day philosopher, a guy named Will Durant, thought should be the aid of observation, not its substance. Now, three things inspired Bacon to set on this path of his. One was the discovery of printing. Now, think about it. The printing press, the spreading of knowledge, the ability to reproduce books in great quantities so that everybody could be part of learning instead of just a chosen few. Another, the discovery and use of gunpowder. Think of how important that was in warfare. Obviously, for the Spanish Armada, or the defeat of the Spanish Armada by the British, is extremely important. And yet another invention, the compass. Now people could get around on the surface of the earth and at least know where they were to some extent. So he saw that some inventions had come along and greatly aided the lot of mankind. And his question was, well, if these three things can do something valuable, what more lies out there yet to be discovered that could help us even more? And again, that's obvious to us. We sit in lit rooms that are air-conditioned, and we drive automobiles, all these discoveries that he couldn't foresee. He at least felt that if we developed the right processes of the mind, we could create these things. So, I'll repeat. What is his method? One, you want to make note of this. This is something I can test you. One, the observation of nature. Experimentation with nature. And in that way, he's directly kinship, directly a brother to Galileo. And two, a new method of thinking about nature. There, he goes beyond Galileo. Galileo was no doubt doing this, but Galileo didn't write it down. Galileo didn't make it explicit. And this new method of thinking brings up a new word for your vocabulary. A system of rules for thinking is called an organum. So he's going to write a new organum, or in Latin, novum organum. That's the meaning of the book. And as a matter of fact, if you go and read what I've asked you to read, the first two aphorisms of the novum organum essentially lay this course out. All right, let's read it a little bit. What I'm going to do today is first talk about the preface and maybe a little bit of the aphorisms. And then next time, we'll look more deeply into the aphorisms. And I'm going to read you some quotes that I think are particularly relevant. You might want to get out your reading. You might want to go to the beginning of the Novum Organum. I'm going to read the preface. It says, page 455 on the bottom. You know, while you're finding it, how many of you, when you read a book, read the preface? Yeah, it's kind of weird. Most of us skip over the preface and want to get to the book. But when you think about it, here's some person who spent a few years of their life writing a book, and when it's all done, they sit back, they open up a beer or something like that, they put their feet on the table and think, wow, is that hard? And they think, you know, I ought to write just some sort of introduction to everything, just to kind of let everybody know why the heck I bothered to walk across Asia. And that's what writing a book is like. So really, there's a lot to be found in a preface, and there's a lot to be found in Bacon's preface. So here we go. I mean, it's just a great beginning. I just love it. First, I'm a scientist. I'm that way. I hope I can make you love it. Here we go. Those who have taken upon them to lay down the law of nature as a thing already searched out and understood, whether they have spoken in simple assurance or professional affectation, have therein done philosophy and the sciences great injury. Yeah, like we already know, get real. That's a great injury to think we already know. For as they have been successful in inducing belief, double underline that, so they have been effective in quenching and stopping inquiry. There it is. Belief versus inquiry. There it is. That's what I've been trying to say for the last handful of weeks. Inquiry, that's what we need, not belief from authority. He then goes on and writes about other people think absolutely nothing can be known. They sort of give up on even trying to understand things. He says that's not a good course of action either. If we dig further into this thing, let's see where else I might want to read. Certainly pay attention to the beginning paragraph there. Oh, I like this one too. I'm on page 456, the beginning of the second paragraph, where he starts talking about his method. Now my method, though hard to practice, is easy to explain, and it is this. I propose to establish progressive stages of certainty. That's great, right? In other words, you go out, you learn a little, then you do experiments, you learn a little more, you narrow in your ideas, you get better and better. But it's hard to reach an ultimate certainty. That's really what he's saying too. We can know things progressively better and better, but can we ever ultimately know everything with perfect certainty? I think he says probably not. You know, I just lectured to you about how mass is invariant. Your mass will always be the same. Your weight might change, right? We talked about that. But your mass will always be the same. That seems like a pretty self-evident thing. But you know it's not true. It's only one stage of certainty. We didn't know until 1905 that mass would change. Do you know what happened in 1905? Some of you know, I'll bet. Einstein's theory of relativity was published in 1905. And he showed that if you go real fast, your mass increases. Mass is not invariant. Son of a gun. Stages of certainty. Never bet the whole house on anything. What else can we do? Well, then he goes on and gives an analogy. He doesn't like logic a whole lot because logic just applied to itself can lead you in spinning little circles like a dog chasing its tail. Here's another one that I particularly like. I'm on page 459. So we should read this to when scientists get their degrees to inspire them. Listen to this. I'm going to start. Well, I guess I'll start at the end of the paragraph about the third line down. Let there be, in short, one method for cultivation and another method for invention of knowledge. And then he talks about those who could do either. And I might add, what does it mean to cultivate knowledge? It means to apply it, to use it. You might say those are like the engineers, and that's certainly an admirable thing to do. The invention of knowledge would be more the scientific thing, to go out and try to find new things. And now I'll read the second paragraph. And for those who prefer the former, that's the cultivation of knowledge, either from hurry or from considerations of business or from want of mental power. I wish Terry King, the Dean of Engineering, was here right now. To take in and embrace the other, which must needs be most men's case. In other words, most of us do have limitations. I wish that they may succeed to their desire in what they are about and obtain what they are pursuing. He wishes them well, but here it comes. But if any man there be who, not content to rest in and use the knowledge which has already been discovered, aspires to penetrate further, to overcome not an adversary in an argument, but nature in action, to seek not pretty and probable conjectures, but certain and demonstrable knowledge, I invite all such to join themselves as true sons, and in modern politics, daughters of men. All right, so there's some good stuff. You get on to the aphorisms. If you don't know what an aphorism is by now, you can pretty much figure it out by example, right? It's a short, concise statement of some sort of truth. These things are real hard to read. But if you look at the first two, you can see what I've been trying to tell you about his goal in this Novum Organum. I'll read the first two. Man, being the servant and interpreter of nature, can do and understand so much and so much only. You know, he writes things kind of backwards, doesn't he? He's got the only at the whole end of the sentence. Only as he observes, in fact or in thought, of the course of nature. Beyond this, he neither knows anything nor can do anything. So, in other words, it's only what we observe is what we know. Beyond that, there's nothing tangible. So he's advocating observation. And then second aphorism, neither the hand nor the understanding left to itself can effect much. It is by instruments and helps that work is done, which are as much wanted for the understanding as for the hand. In other words, he's making an analogy here. Yeah, if you want to do something by the hand, an instrument would help. If you want to observe the moons of Jupiter, you need a telescope. Right? If you want to measure pressure, you need a pressure instrument, right? But there's more here. He says the intellect needs an instrument. And the last sentence, so the instruments of the mind, either suggestions or understandings or cautions. I didn't say that very well, but let's just go back. So the instruments of the mind. His purpose here is not to give us scientific instruments, not telescopes like Galileo gave us, but instruments of the mind, processes of thought, so that we can properly interpret nature. All right, I'm going to stop for now. That's enough philosophy. 20 minutes of philosophy. That's more than I can like. Keep struggling into this. Again, I know that it's hard. When I write test questions, I'll pick the most prominent things. If you want to blow over something because it's so boring and you think Sorensen would never ask test question on this, you're probably right. But at least make the endeavor here. And head for, pay attention for, aphorism 39. Because in aphorism 39, he introduces something that's well known to all people of education, and those are the idols of knowledge. There are 4 idols of knowledge. See if you can figure out, it's not the normal use of the word idol. See if you can figure out what it is. These are warnings about what not to do with your mind. We'll talk about that in this study.
Being a non-scientist and having read what I've read and having done that, that seems like a pretty scathing report to anyone who doesn't delve into nature, who doesn't try to observe all they can, who doesn't do all these things, who doesn't question what they've been told, who doesn't question necessarily the reason for what they've seen. But being a non-scientist, it seems that scientists are the people who are worse, that fall short of that the most. I mean, are scientists, our physicists, are the different sciences still studying why gravity works? Are they still studying all the things that they teach in elementary science classes? They teach us as truth. Are they still studying those things to see if they're right?
Yeah, I would hope that when I lecture to you and tell you things, I would hope that you always remember that I'm saying, as far as I know now, mass is invariant. You have to do that as a scientist because it'd be so easy to get ambushed by real facts later on. I think it's kind of interesting that you react that way. I think you're right. That if you read the popular literature, you read the newspaper and it will say, scientists say, blah, blah, blah. And by putting the scientists say in front, boom, authority. This has got to be true because scientists say it. Okay? It's not mom said it or dad. Scientists say it. Right? But that's the journalist. Give me a break. If I say something, I'm going to qualify it. And any good scientist will qualify it. And that's the marvel of science, is that if you keep your eyes open, you'll find new things. Then again, you've got to have some certainty. For a long time, people had to say mass is invariant because it solved a lot of problems. There was a lot of good technology developed on the idea that mass was invariant up to 1905. Like we flew airplanes by 1905 on invariant mass. Then we come along and find out son of a gun, mass isn't invariant. We do experiments. It was a theoretical prediction.
Yeah.
If we do experiments and find out it's right, we marvel at the result, and then we include that. We make one more step, stages of certainty. And another thing is, let's not be scathing on anybody who doesn't want to be a scientist. There's plenty of great things to do in this world. But if everything you do, I'll bet it will help you to have a scientific attitude. Not take too much for authority. Always question a little bit. Of course, I'm a product of the late 60s, right? We questioned authority up to wazoo. And for a good thing. I think it's glad we did. But you don't want total anarchy. You've got to have some confidence. That's a great question. Any other questions? All right, well, let's get back to something I know better, which is physics. I'm going to talk about rotational motion, which is chapter 8. The first thing I want to talk about is how hard it is to rotate some things, how there's an analogy to mass and rotational motion. Remember, mass was essentially the resistance to acceleration. The more massive something was, the harder it was to accelerate. So I've got here a couple of batons. I've got a red one, and let's just prove to you that they have the same mass. I guess I have to hold it here. It looks, what, maybe 14 newtons or so? So that's its weight. Take this blue one. And again, same weight, 14 newtons, so it's the same mass. Okay? So now, the question is, there's certainly the same amount of acceleration, but what about wiggling these things? What about rotating these things? Okay? So I need 2 volunteers from the audience. Here's one. You can take this one, hold it right there in the center. And I need another volunteer. How about a man? How about the guy who just wiped his eye? How about you coming down here? And we're going to have a contest. Okay? What I want you to do is rotate this. Women, of course, are better baton twirlers than men, so we're going to test that hypothesis. Grab it right there. Both of you face each other. Extend out. And then when I say go, I want you to see who can swivel this thing backwards and forwards quicker. Ready, set, go. Why do I always get wimpy girls? Give me that one. Let me try this. That guy doesn't look that tough. Ready, go. Okay, huh? Here, you try it. Ugh. I can't even move it. Ready, go. Yeah, he's got me. What do you think the difference is? What do you think the difference is? They weigh the same. Same length. Just wait. They don't feel like they weigh the same. Yeah. But it's the distribution of mass. We got more mass on the edges out here. All that mass is in the center. So when you try to rotate this, even though it's the same mass, all the mass is out here, and it's harder to do. Much like a baseball bat, right? If you put a lot of weight at the end of a baseball bat, it's a lot harder to swing, but of course, if you can swing, you can really drive the ball. All right, well, that's an attempt to demonstrate that rotational inertia, right? The inertia for rotational changes depends not only on the mass, but where the mass is. Farther from the axle, the harder it is to spin. You know, I can kind of demonstrate that in another way, and that's with a hammer. Now, this hammer has a center of gravity right about there, right? That's where I can balance it. And so, relative to its geometric center, obviously there's a lot of mass on one end or the other. And this hammer is harder to swing this way than it is this way. It's the same hammer, but it's much easier to swing like that. And you can actually demonstrate that if you think about balancing. Because if the thing's going to balance, it's going to rotate out of balance, right? And if we rotate around this end, it ought to fall slower than around this end. And you might notice that if I try to balance this thing. This is not easy to do, okay? But that's real easy to do. And in fact, since it's a camera. And why is that? Because the mass is a long ways away from the point of rotation, so it's slower, and I can keep my nose with it. Okay? When you walk on a balance beam, you're going to walk on some beam here. I should have brought a 2x4 out. But how do you balance yourself? You stick your arms out, right? Why is that? Your mass doesn't change, but as you extend yourself, the mass now is farther away from the point where you're trying to balance, and so you can balance better. What do tightrope walkers do? They grab a whole doggone bar, don't they? And this bar is real long, and that gives them stability because the bar is hard to rotate. They won't rotate off the balance that they're trying to keep. So the first concept we have to get here is this concept of rotational inertia. Remember, inertia is essentially a resistance to change, so this is a resistance to rotation. Now this is analogous to mass. Right? Mass is a resistance towards motion in general. Right? So massive things are hard to move, whereas things with large rotational inertia are also hard to rotate, to change their rotation. I can demonstrate that yet another way with a race. If I remember right, test this out. These two things, you can barely see it, looks like about 4 or 5 newtons. Okay, so they got the same mass. And I'm going to roll them down this inclined plane, right? Now I want you to think in terms of rotational inertia. Same mass. Which one do you think has the bigger rotational inertia? Let's vote. Does this have the bigger rotational inertia? And we'll find out if they're asleep. If nobody votes on this, I'm out of luck. Or does this have the bigger rotational inertia? Very good, because the mass is further from the center, right? It's like a flywheel. You've all heard of flywheels, right? All right, so if we're going to have a race, where's your money? Who's going to win the race? All right, so who puts $1 on the wood disc? Okay, who puts $1 on the metal ring? But wait a minute, the metal ring has more resistance to rotation. The one with the smaller resistance to rotation wins. If we have two discs, it should be a tie, right? See, stages of certainty. Every once in a while, something doesn't work. All right, so that's your first concept, rotation. Now this would make a good test problem, all right? Good test. All right, we need a way to make things rotate. Who knows what that is? When you try to take the lid off of a ketchup bottle, what are you doing to the lid of a ketchup bottle? You putting a force on it? Kind of. And forces make things move linear. How do we make things rotate? There's a T word. Torque it. Torque it. How do you take a nut off of a bolt? You put torque in it, right? What's a torque machine? If you walk into the hardware store and ask for a torque machine, what will you get? A weird look. But what should you get? Wrench. Is that a great wrench? You can really torque it this way. I love that wrench. I like that almost as much as my lead weight. How do you use a wrench? Well, you know, you got a nut. Lost a hex nut here. And you put the wrench on there. Right? And you know what they do at KU? They push on the wrench. Where'd you get your undergraduate degree?
Baylor.
You know what they do at Baylor?
Baylor.
Is that in Texas?
That's in Texas. They won in football last week. I want you to know that's a miracle.
They won?
Is that when they played in Manhattan High? Here's what they do at Baylor. They push down here. Okay? Now that's a little better. Where should you push on this wrench? You want to come up here. You want to get to the end of the handle, and you want to push perpendicular. You want to apply a force that's perpendicular. Like this is a force too. We're clear out here on the end of the handle, but that's not going to do anything for torque. So torque needs both a force and it needs this distance. The book likes to call this the lever arm. So let's see if I can squeeze it all in here. Lever arm, which kind of makes sense. It is like a lever, isn't it? So the torque is actually dependent upon two things. It's the force times this lever arm. The bigger the force, the bigger your torque, the bigger your lever arm. You know, if you got a stuck nut and you can't quite get it off, what do? You put a hunk of pipe on your wrench, right? You get way out here and then you really crank on it. You hope you don't break your wrench or anything like that. You know, you've done this before too because you've all played with teeter-totters. I got a fulcrum here. A teeter-totter is just a torque device. I'm going to put this ruler here, right about in the center. And then I'm going to get some forces with some simple masses. So if the masses are the same, and I put it at each end, right, I mean, think about it. This mass has a force down on it due to gravity. We've got a distance, so there's a torque. Right? And if I put a mass over here the same amount, I got the same force, the same distance, so I have the same torque. And it should balance. And it does. I have to do a little adjustment. You can see it balances. Now you also know that if I come along with a bigger mass, and I put it out here, what's going to happen? Right, this is like the schoolyard bully. You know? What's going to happen? Oh, bang, you know, you're stuck up in the air. I can't get down. Some sixth grader, you know. So what do? You got to rebalance it. You can do this. Let's see, this thing's moved on me. Closer. Okay, you can see I was almost there. All right, you can see I'm real close to balance. But the thing you want to notice here, big force, little force. Big force times smaller distance equals little force times bigger distance. That's the thing you want to remember, is this qualitative distance. Force times distance is your. All right, the last thing I think I'll be able to talk about today on rotation stuff is something that's really neat. It's this idea, oops, I probably shouldn't have erased that, but I already have. This idea of centrifugal force. Whenever you think of rotational motion, I think you think of centrifugal force. If I take this beanbag, for instance, and spin it around in a circle, okay, you know the beanbag is trying to escape my hand. If I let it go, the beanbag would go flying off, right? This bag is pulling on the string because of the centrifugal force. Certainly, you know, you experience that in a car. If you're sitting in your car and you're driving along and you're going down the road and you turn the wheel to the right, what do you feel? So I turn the road, I'm trying to turn to the right, what happens? You get pushed out of the way, right, by the centrifugal force. It has great practical application. Matter of fact, Janet, could you help me demonstrate centrifugal force? When I was 16 and just learned to drive, Janet, you sit right here. I learned to drive with a 57 Ford, 287 engine, 4-barrel carburetor, Eagle Gold in the left. My dad's car. And back then we used to have, remember the seats, they were like sofas? Yeah, they didn't have bucket seats. And we had vinyl upholstery, so there wasn't much friction. And every long once in a while I get lucky enough that I have a girl. And you know, you're trying to drive her along being cool, you know how science goes. Never tell a girl you're interested in science. And you know, you got to figure out some way to kind of break the ice. And, you get your arm up on, you didn't need to put it up there, but you got up there on the seat, you know, and you're looking for a turn to the right. You know what I mean? Yeah, you're looking for a turn to the right, and there's a turn to the right. Here's your speed up. And then you're right, you turn to the right, and she skitters out over here, and you got it. You sit in the back of the pickup. But again, it emphasizes this concept of a centrifugal force. If you're going around the curve this way, she gets pushed out towards you, and you're even getting pushed towards the door, right? You got this force pushing away from the center. Or so it seems. Now, most of the time I was alone in that 57, which gave me a lot of time to think about the situation. And it occurred to me that when I hit that curve and I start to go around the curve, my body really wants to keep going in a straight line. I should be going in a straight line. What the heck? I did experiments. Young gal laughing. I rolled down the window and I had a rock, and I'm going along and I turned the car and I let the rock go at the same time, and my car went this way. Which way did the rock go? Kept going 30 miles an hour. And I thought, gee, it takes a force to change velocity. It was going 30 miles an hour west. In this car, I'm going 30 miles an hour west, and then I end up going 30 miles an hour north. Did my velocity change? Yeah, remember, we're trying to differentiate between speed and velocity. My velocity changed, even though my speed didn't change. And if the velocity changed, do you have an acceleration? And if you got an acceleration, according to you-know-who's second law, do you have to have a force? Which direction is the force? If I'm going this way, and I turn this way, the force must be pulling me in, not pushing me out. What the heck is going on here? Let's draw a picture of this again. And this is really subtle, but I really want you to know this. Let's draw the roadway. So this is a bird's eye view of the roadway. So we're looking down. Okay. And here we are in gold and black. Okay. Sitting here, let's get rid of the windshields. Come over here. And we're about to hit this turn. And here I am. And here she is. Red for symbolic reasons. And what's going to happen? What's going to happen? This car's going to go into this turn. And if there's no forces on her, if her bottom, okay, and the seats have no friction between them, okay, what's she going to do? If there's no force on her, according to the first law of Newton, she continues, she remains, remember that? In a straight line motion with constant velocity. She's going to keep going this way if there's no forces on her. Okay? And what's the car going to do? Well, the car is working its way around the turn. And here I am, and here she is. She appeared to be forced out toward me, but she wasn't. I was forced in towards her. I moved into her. What moved me in? The door. I'm sitting there, I can feel the door pushing me. What happens if the door gives way? We both end up here on the milo field together. Okay? Yeah, there's a force not outward. This is bogus. There is no centrifugal force. The F is wrong. Okay, this part is wrong. Centrifugal means to push away. There is, in fact, what's really going on, what we call a centrifugal force. A force towards the center. Let's make sure I get that down. Matter of fact, I think centripetal is like Greek for center seeking. I kind of forget. Force toward the center. You have to have it to have circular motion. She doesn't have a centrifugal force because her bottom has no friction on those vinyl seat covers my father had, and she keeps going straight. On the other hand, the door is pressing on me. Which way is the door pressing? It's pressing this way on me. forcing me. Notice it's towards the center of the circle, forcing me to go in a circular motion. Let's go back to the beanbag. Where did I put the beanbag? I mean, look at the beanbag. If this thing's spinning along, why does it go in a circular motion? Let's catch it up here at the top. It's coming across like that. It's trying to go north. But look, I'm pulling down. Right? I'm pulling toward the center all the time. Now it's trying to go down. Keep on going, but no. Instead of having that chance to go down, the string pulls it down like that. Now what is this? The string is pulling this. What's it doing to the string by the third law? Pulling out, and that's where you get faked out. Yeah, the doors, I go around the turn like this way. The door is pushing me into the turn. There's the centrifugal force. With the third law, I push back, don't I? I have to whether I try to or not. So it's me pushing back that makes me think there's a force pushing me out. But that's not true. And as soon as the centrifugal force is gone, as soon as that door opens, I'm out of luck. Because I leave the car and travel straight out. And is this important? Well, what keeps the moon going around the Earth? What keeps the Earth going around the sun? What keeps the electrons, every atom of your body, going around the proton? There's a force of attraction between the Earth and the sun, gravity. If you turn off gravity, the Earth goes flying out into space on a straight line. But you keep gravity on, and it's analogous to the string, constantly pulling the Earth towards the sun. There's a force of attraction between electrons and protons, the electrostatic interaction. If you turn that off, all the electrons would take off, and it'd be real hard to walk home. All right, I'm about done. Next question. All right.